Hey everyone, and welcome to this explainer on bandwidth utilization. Since you're all undergraduate engineering students, I know you already understand the basics of data transmission, but today we're really going to get into the weeds of how we maximize it. We're going to treat bandwidth exactly like a limited physical highway, and we're going to look at the brilliant engineering solutions used to pack as much data traffic onto that highway as possible, literally without causing any collisions. Look, whether you're eventually designing massive telecommunications networks or you're fine-tuning long-haul fiber optic lines, mastering how we divide and conquer our transmission media is absolutely crucial. So let's get into it. Okay, so here's our roadmap for today. 1. Link versus channel basics. 2. Analog frequency and wavelength. 3. Digital time-division multiplexing. 4. Efficiency with statistical TDM. And finally, number 5, spread spectrum techniques. All right, let's kick things off with Section 1, Link versus Channel Basics. So before we talk about complex multiplexing, the absolutely crucial starting point is understanding the fundamental difference between a link and a channel. They are not the same thing. Think of the link as the actual, tangible, physical path. It's the copper wire you can hold in your hand, the fiber optic cable buried underground, or even the air itself in wireless communication. That is the physical asphalt of our highway. A channel, on the other hand, is completely logical. It's the logical portion of that link dedicated to carrying one specific transmission. These are the designated traffic lanes painted right onto that asphalt. So we only have one physical pipe, but through the magic of multiplexing, we can logically carve it up to carry multiple simultaneous streams of information. Now, this concept perfectly illustrates how we actually achieve that division in the real world. We use a multiplexer, usually just called a mux, on the sending side, and a demultiplexer, or demux, on the receiving end. Going back to our analogy, think of the multiplexer as the highway on-ramp. It performs a many-to-one function. It takes n number of input lines and brilliantly combines them so they can all share a single, high-capacity physical link. Then, way down on the other end, the demultiplexer acts as the off-ramp. It does the exact opposite, a one-to-many function, separating that dense, combined stream back into its individual component channels and routing them safely to their proper destinations. Moving on from the hardware to the methodology, we can categorize our multiplexing, our network traffic control methods, if you will, into 3 main types. And this is based entirely on whether the signals we're dealing with are analog or digital. For analog signals, we utilize Frequency-Division Multiplexing, or FDM, and Wavelength-Division Multiplexing, WDM. For digital signals, our absolute go-to method is Time-Division Multiplexing, or TDM. This taxonomy tree dictates the actual hardware and the mathematical approaches we're going to use to combine our signals. Which brings us nicely to Section 2, Analog, Frequency, and Wavelength. Okay. Let's talk about Frequency-Division Multiplexing, or FDM. This is an analog technique, and it can be applied anytime the bandwidth of a link is greater than the combined bandwidths of the signals you want to transmit. It is literally like painting distinct, permanent lanes on our highway. Every single input signal gets its own dedicated carrier frequency to travel in. If you look at how channels are mapped out in FDM, channel 1, channel 2, and channel 3 are basically stacked vertically in the frequency domain. They are all traveling across the wire at the exact same time, but they exist in completely different frequency spaces. They are completely unaware of one another. Now, to make FDM actually work, the communication engineering process requires a very specific, strict sequence. First, the baseband analog signals are generated by the source. Standard stuff. Second, modulators step in and shift these signals up to distinct, non-overlapping carrier frequencies. Third, these shifted signals are mathematically combined, or summed together, into a single composite signal that travels across the physical link. Then, once it arrives at its destination, the fourth step is for the demultiplexer to use incredibly strict bandpass filters to isolate each specific frequency band. And finally, demodulators strip away those carrier frequencies, shifting the signals back down to restore the original baseband data. You can really visualize those steps in action. Modulators grab distinct baseband signals. The circuitry essentially multiplies these baseband signals with completely unique carrier frequencies. Let's call them F1, F2, and F3. That data actually modulates the wave. The summation node then physically adds these continuous waveforms together. The end result is this dense, highly complex composite waveform that utilizes the full capacity of our transmission link. It's a pretty elegant solution. But as engineering students, you know there's always a catch in the real world. Here, the physical danger is frequency drift.
To keep our virtual cars in their lanes from sideswiping each other when frequencies naturally drift, we have to engineer what are called guard bands. These are strips of totally unused bandwidth that act exactly like concrete highway dividers to prevent signal overlap and nasty interference. To put that into perspective, if we have 5 channels that each require 100 kilohertz of bandwidth and we insert a 10 kilohertz guard band between each of them, that's 4 gaps total, we'd need a total link bandwidth of 540 kilohertz. So yeah, it costs us a little bit of overall bandwidth overhead, but it is non-negotiable for ensuring total signal integrity.
All right, moving right along to Section 3, Digital, Time-Division Multiplexing. So time-division multiplexing, or TDM, leaves the analog world behind. This is a strictly digital process where several connections share that high-bandwidth link sequentially. Think of this acting much like an automated traffic light at a really busy intersection, giving equal green light time to different incoming roads. Instead of taking up a tiny fraction of the bandwidth all of the time, like we just saw with FDM, TDM takes up all of the available bandwidth, but only for a fraction of the time. We are combining several low-rate channels into one high-rate channel by organizing the data into very distinct timeframes. The best way to visualize this interleaving process is to picture 2 perfectly synchronized fast-rotating switches. One is sitting at the multiplexer, and one is at the demultiplexer. And they rotate at exactly the same speed. As the switch at the MUX rotates, it opens a connection, grabs a unit of data, that could be a bit, a byte, or whole block, from each incoming line, and places it squarely onto the output link. The switch at the DMUX rotates in total harmony to grab that exact unit off the link and distribute it to the correct outgoing receiver. It is a highly orchestrated, completely unvarying pace.
But I'm sure you've already spotted the problem. There's a massive, glaring inefficiency in synchronous TDM, because that slot allocation is perfectly fixed and rigid. If a road has no waiting cars, the traffic light still turns green anyway. If a source device has absolutely no data to send at that exact microsecond, the rotating switch simply grabs nothing, resulting in totally wasted empty slots traveling all the way across our transmission highway. In modern bursty data networks where traffic is wildly unpredictable, this rigid pre-allocation means we are severely underutilizing our very expensive bandwidth. And that leads us to the solution in Section 4, Efficiency with Statistical TDM.
When you compare these multiplexing strategies side by side, it's pretty eye-opening. FDM permanently divides the pipe by analog frequency lanes, totally regardless of whether there's traffic or not. But statistical TDM, it dynamically slices the pipe by time, and it intentionally skips over any silent lines. If 2 specific lines have nothing to say, a statistical TDM multiplexer simply doesn't give them a time slot in that frame at all. It packs the frame exclusively with active data. This is huge because it means the total capacity of the link can actually be less than the sum of the capacities of each input channel. Why? Because statistically speaking, they're almost never all transmitting at peak capacity at the exact same moment.
This dynamic slot allocation is a real game changer for overall network bandwidth efficiency. But, as we always say, engineering is all about trade-offs. Because the slots are no longer rigidly fixed to a specific input line, the demultiplexer on the receiving side doesn't inherently know where a piece of data came from or where it's supposed to go. Because of that, statistical TDM requires us to attach addressing overhead, essentially a tiny routing tag, to every single payload. However, the massive efficiency we gain by completely eliminating empty slots totally outweighs the minor cost of having to add these destination addresses.
Let's wrap up the technical deep dive with Section 5, Spread Spectrum Techniques.
Okay, entering the world of spread spectrum is really interesting because it intentionally breaks the golden rule of communication engineering, which is to conserve bandwidth. Instead of saving space, it takes the original signal bandwidth and drastically expands it to a much, much larger frequency range. It does this using a pseudo-random spreading code that is entirely independent of the original signal itself. The result? A signal that looks like absolute random background noise to anyone who doesn't have the exact decryption key. It's incredibly secure.
One really clever way we achieve this is through frequency hopping spread spectrum, or FHSS. Instead of transmitting on one predictable carrier frequency that anyone could listen to, a pseudo-random noise generator forces the source signal to constantly hop between dozens of different carrier frequencies many, many times a second. It's literally an elaborate game of whack-a-mole. If an adversary tries to intercept the data or a jammer tries to block the transmission on one frequency, it doesn't matter. The signal has already hopped to another frequency. Only the authorized receiver with the exact same pseudo-random sequence can reassemble those chaotic hops back into a coherent message. Alternatively, we have direct sequence spread spectrum, or DSSS. Rather than hopping around different frequencies, DSSS replaces every single original data bit with a highly complex mathematical string of chips. For example, a single digital 1 might be multiplied by a highly specific pattern, like an 11-bit Barker sequence. Now, this dramatically expands the data rate and therefore expands the bandwidth by a factor of 11. The genius here is that if ambient interference or a malicious jammer corrupts a few of these chips during transit, the receiver has enough redundant mathematical information to fully recover the original bit anyway. It provides massive, built-in immunity against interference. All right, as you wrap up your studies on these fundamental multiplexing systems today, I want to leave you with a real-world problem to ponder. We've seen how FDM gives us strict analog lanes, how statistical TDM gives us brilliant digital efficiency, and how spread spectrum provides robust security through complex mathematics. But if spread spectrum relies on pseudo-random codes to hide our data in plain sight, how will tomorrow's quantum computing capabilities, which theoretically can easily crack such pseudo-random codes, force us to invent entirely new traffic rules for the communication highways of the future? It's a massive challenge, and it's one you'll be facing as you design tomorrow's networks. Think about it. Thanks for joining me in this explainer, and I'll catch you next time.